Is Xinyu, who has recently joined us in Oxford, previously was at UC Berkeley, and is going to speak about alpha potential games.
Thank you. Thank you very much for having me here, and thanks for all the organizers to organize such a wonderful workshop. So today I want to share some of our works on alpha potential game framework, how we use it to study multiplayer games. And this is based on the joint work with my PhD advisor Xinyu from Berkeley, and also Yufei over there. Yeah. So I will start with some background and motivations, some history on the static potential games, and some recent advance in the dynamic potential games, especially in the multi-agent reinforcement learning, and then talk about our result of alpha potential game framework. And later I will give a case study to how to apply those results in the second part into a more concrete case study problems. And eventually I will conclude a little bit how we use this framework for the general stochastic differential games. Okay, so here we consider a scenario where we have n-player games. So such scenarios exist in many different applications, including economic, political, and engineering environments. And one of the very important concepts is the Nash equilibrium. So we are looking for a set of strategy such that no one wants to change their own strategy based on the current strategy profile of everyone else. And it's known to be hard to analyze due to the interdependence among the players. And previous line of the research, including mean field games or graphon games, where they assume that all the players are homogeneous. They have the same cost structure and probability transition structure, such that they only need to study for mean field games. They only need to study of one of the representative players. And both mean field games or the recent graphon games, they more or less focus on scenario when the number of players, this n, is quite large, to study the asymptotical behavior to get a mean field approximation to the corresponding n-player games. So here we want to look for a different line of the research where we focus on only n-player games, only finitely many player games. And we hope that those players can have certain levels of heterogeneity. So here I want to give a brief review on the potential game by this pioneer work. Here it is a setup of so-called static game. It's like when we play rock paper scissors. We just play this game for one time and that is. So there's no state transitions at this moment. So here we have n players, and I use this AI to denote the strategy of player I, and those just denote the joint strategy profile of all the players. And this notation in this talk just denotes the joint strategy of all the other players except player I. And here each player has a value function depending on the joint strategy of all the players, and it will yield a value of the value given by this value function. And in this work, they proposed such a game called potential game. They said that if there exists some common function phi, such that the difference by changing one of the control components, this difference is so if player I changed her own control, and this difference can be captured by the difference in a common function, then such a game is called a potential game. So why this structure is very important and very nice? Essentially because if we think of the scenario that, for example, current action profile A is the optimizer of phi, then what happens? If you change it into AI prime, then it will end up into a worse value than phi. And because of this difference is equal, then player I wouldn't want to change her own control. And it is same for all the players. So in that sense, any optimizer of the potential function is a Nash equilibrium. Therefore, it reduces the problems of finding the Nash equilibrium of the game into minimize one single function. So that is the case structure here. So this framework has been popular to study the heterogeneous player because it doesn't require the players to be identical. And because of the nice structure of the potential function, it reduces everything into minimize one single function. So there are some algorithm development in this domain, such as algorithm for best response or fictitious play. They can show that they converge Nash equilibrium. So here, a key question is that what is a potential function? For given if we have an n-player game, do we know that whether it is a potential game? If it is, what is a potential function? How to find it? So in their work, so I just quickly review a very simple case here. Suppose that the action set is just the R, and the value function is just smooth enough. In this case, the work gives a classical construction of the potential function. So it says that a game is a potential game if and only if the second order derivative matches. And in that sense, a potential function is given by this form. So essentially, it is an aggregation over the action space, starting from a physical control profile into the one that you are trying to evaluate. So it's take a integration with respect to the first order derivative over the action space. So that is the construction of the potential function in a static game. So a natural question is that can we extend sort of those ideas to dynamic games? So in dynamic games here, we have a component of the system state transition. Now each player wants to optimize his or her expected cost, where the cost depending on both of the state evolution and also all the players' actions. For example, in the self-driven car, each agent wants to move to their different targets. They have their own different cost, while at the same time they need to be cautious of the system and to avoid the collision. So in dynamic games, one of the attempts to adapt the potential games is introduced by this nice work on macro potential games. So they study a scenario where they consider discrete time state transitions with Markovian transitions and Markovian policies. So which is just a macro decision process that is a benefit to study the multi-agent reinforcement learning. And they propose that they call a game to be a macro potential game by generalizing this definition from the static setting to the dynamic setting. That if your change in the value function, so here now the strategy set is Markovian control. If this change for any value functions can be captured by this common function phi, then such a game is called a macro potential game. So with this definition, we still have such a properties that any optimizer of this potential function phi is just a Nash equilibrium. And there have been many algorithm development in multi-agent reinforcement learning, such as policy gradient or some based on the best response, where they can show that they have convergence to the Nash equilibrium for the case of macro potential game. So it looks very nice that you have algorithm convergence guarantee, but does this setup has any limitations? So indeed, the authors in the previous paper, they showed that most of the games, even with Markovian transitions and policies, are not MPG. And even they gave a very concrete case to show that even at each step, we are a static potential game overall because of the existence of the state transition. Overall, the game is not a macro potential game. There are very concrete counterexample here. And also because here your definition is defined in terms of the policies, it's actually quite hard to certify whether a game is a macro potential game or not, and what is a potential function. It's not easy, not clear how to find the potential functions. So therefore, we want to have a more general form of potential games to study dynamic games. Okay, so here I want to briefly introduce our framework. So just quickly rephrase the setup. So now compared with the static games, we have additional component on the state space. And this is denoted as the objective function using the action profile of all the players. And here we assume that we start from like a fixed initial state. And we assume that each player wants to minimize their objective function in this case. And our idea is pretty simple and straightforward. So we call a game an alpha potential game if you can find some function phi such that this difference, instead of 0 now, this difference just can be bounded by some constant alpha. And then we call such a game an alpha potential game. And we, just to highlight the dependence on alpha, we call the corresponding function phi as an alpha potential function. And so far I haven't specified any state transition. So actually this setup can work with both discrete and continuous state transitions, and also can work with open loop, closed loop, and Markovian controls. But in this talk, I will mainly focus on the open loop control. So here, the first straightforward proposition is that now if you have a minimizer of the alpha potential function, instead of saying that this minimizer is a Nash equilibrium, we still can conclude that it is an alpha Nash equilibrium because now we have those gap alpha. So it still reduces the problems of finding a Nash equilibrium into minimizing one single function into a stochastic control problem involving this alpha potential function. And because here we have sort of have some flexibilities, this alpha Nash equilibrium can allow us to study a broader class of problems that beyond potential game. And we will see that this alpha, the value of alpha, actually depend on the model parameters such as cost structure, policy class, or number of players very explicit. Yeah, so here I want to just briefly talk about where is our works. So I just reviewed the static potential games from those pioneer work. And in recent years, people also did some works on static near potential games where they studied a static game, but they also allowed certain gap there. And in the recent years, with the popularity of multi-agent reinforcement learning, this is a very incomplete citation. There are a lot of the research working on the macro potential games and algorithm designs. And this is one of our previous work where we study alpha potential game in a macro decision process setting. And we have some algorithm design. And for the recent work, in one of the work by Xinyu and Yufei, they proposed some analytical framework to study potential games, where we now focus on the setting instead of macro games. We more or less focus on the setting of stochastic differential equations, the game governed by stochastic differential equations. And this is our focus about studying the alpha potential games in this setting. Okay. Okay. So first, since we talk about the alpha potential game, the first natural question is that what is potential function? Can you construct a potential function? So indeed, here we did a construction that quite analog to the static potential game. So here we use this integration with respect to first order linear derivative. I will give the definition just in a minute. And then similarly, we do an integration with respect to the action space from a preset control profile into the one that we are trying to evaluate. So you need to do the integration with respect to this line. And with such the construction, a net thing is that we can give an upper bound for the alpha with respect to the second order linear derivatives with respect to the objective functions. Yeah. And here is just a quick review of this definition of linear derivatives. So here, bilinear derivatives, basically, is the limit where we perturb the control AI into another control direction AI prime. This is how we define the linear derivative. And this definition is weaker than the Gauss derivatives, and we do not specify topology here on the strategy class. Therefore, it provides us certain flexibility to deal with different control types and or policy types. Yeah, so now we have this construction of the alpha potential function. Then finding the approximate Nash equilibrium is then reduced to the control problem that optimize this function. Where again, I just want to highlight that here we have aggregation over action space, and it's different to some of the mean field framework where the propagation of chaos is over the state space. Okay. So now, before going to more general framework, I want to give a more concrete case study, how we use those constructions of alpha potential functions into study a more concrete example here. So here we consider so-called crowd motion games. So here we assume that each player have the following state dynamics. So the player I state will be determined by her own control and some Brownian motion. And we assume that each player wants to minimize this objective function. So in the crowd motion games, we model this running cost with the part that depending on the control you use. And also here is the effect of player I depending on the other player's xj's. And we have another terminal cost. So here, this function k models the interaction between player I and other player j. And this qij is a weight to reflect that how much these interactions influence in the player i's value function. And we have different choice for this kernel function. In the case that you want to model a version, so you want to be distant from other players. In that case, one choice is to use the Gaussian kernel, such that if player I and player j's distance is very close to 0, you will have a cost. Otherwise, you will have almost 0 cost. Or you want to model some flocking effects like animal flocking, they want to travel together. One choice is just to adopt a Gaussian kernel. If your distance is very close, you have a very small cost. Otherwise, you have large cost. And for the terminal cost in the crowd motion games, here we just set a very simple choice that, for example, each player have their preset targets and they want to travel to that target. So one of the choice for terminal cost is just the distance norm between the terminal position and the preset targets. Okay, so far I have introduced a setup for the crowd motion games, how we apply the alpha potential framework here. So I just remind everyone that here is our construction of the alpha potential function where we have the linear derivative with respect to the control. And we can compute this first order linear derivatives essentially just by chain rule. So this is a derivative of objective with respect to control, and here you can will it as a chain rule. You do the partial derivative with respect to state, and you can will this y as the partial derivative of the state space x with respect to control u. And indeed, this y, where I sometimes call it sensitivity process, is also follows the following equation here. So, but now here is still some problems into minimizing the function. Because here, in this stochastic control problems, we want to minimize u for this phi u, but here it's governed by an infinitely class of state process, because this x is governed by ru. R is a number in 0 and 1. We do an integration here, so here it involves an infinitely family of state process. So it's not a standard stochastic control problem. However, with the distributed dynamics, we actually can simplify this calculation a little bit by noting that actually in our problems, the XRU can be viewed as some combination between XU and YU. And in that case, if we replace the XRU with these two processes, it's reduced to a standard control problems. Yeah. So here we replace originally the XRU with the combination of state process and the sensitivity process. And here we note that the minimization of the alpha potential function is reduced to a finite dimensional control problem with two state space. One is X and another is Y. Okay, so now before we know how to minimize the alpha potential function, but a natural question is that how large is this alpha? So here we give a very concrete bound for the alpha because the alpha is the asymmetry between the second order linear derivatives. So essentially here we can reduce everything into the asymmetry between the second order derivatives of the running cost and terminal cost. And because we have this concrete structure of the Fi and Gi in a crowd motion game, we have this concrete bound for alpha. So essentially alpha depends on the derivative, the L infinity norm of the derivatives of the kernel function, and also the asymmetry between the interaction weights. So it can be easily found out that if this Qij equal to Qji, if we have symmetric interaction weights, then the alpha is 0. By minimizing the potential function, you immediately get a Nash equilibrium. What if the Qij doesn't equal to Qji in the asymmetric case? So here in the asymmetric case, we consider a network where it's specified from some underlying graph. And we assume that we model the interactions of the players using this graph such that each node is one of the players. And we assume that the interaction between any two players on this graph decays if they are very distant from each other on this graph. And here we assume that there's a bounded degree on this graph such that each player is connected to at most dj other players. So it is not a very dense graph. Instead, it requires certain level of sparsity. So in the case that if the interaction weights Qij decays as the distance between ij, so if it decays exponentially, if this asymmetry decays exponentially, then we will have the following bound for the alpha, and we have this clear bound in terms of different number of players and different sparsity level of the graph. And again, similarly, if the asymmetry between the interaction weights decays polynomially, we still have a concrete bound for alpha in terms of this data here. Okay, so finally, I want to show some numerics here. So as I just mentioned, minimizing the potential function is just a stochastic control problem with two underlying processes. So here, of course, with the dynamic programming and Hamilton-Jacobian equation, you can solve it, and we can get the optimal control feedback in both x and y. So with that intuition, we can design a policy gradient method to find the optimal control U. And we design a policy gradient method and parameterize the control feedback in x and y and do the gradient descent. And here we utilize an architecture, we utilize the ResNet architecture, where in this paper they tested the ResNet with some different time series scenarios. So it's kind of stable in this case. Okay, so now I want to show you some of the numerics results. So this case, we have like an aversion game. So this is the origin, and this is 4 players' destination. So they all want to travel to the same destination, but they do not want to travel with each other. And that is the simulations. And this case, we have a flocking game, where this is a destination of all the 4 players. They have their own this is the starting points of the 4 players, and they have their own destinations. But they want to spend a little bit time traveling with each other. So it's kind of interesting that they somehow found a common ground and then travel to their own destinations. So the previous 2 scenario I showed is that all the Qij equal to Qji equal to 1, so they have like equal dependence on each other. But in this application, I showed that they divided into 2 groups, so they only want to travel with part of the other players. So it's a similar setup, but in this case, the blue players just want to travel with green player, but they has no preference in terms of the position of other players. Okay. Yeah, and here is some more numerical simulations with different noise. So this one is that each player have their individual noise, and I also want to mention that our method also work with common noise. So here I only put some possible common jumps, and you can see that they sort of jump at the same time, but they can also move to their own destinations. Yeah.
So the previous simulations having the sigma to 0. So that's the
Alpha is 0. What is 0?
So the sigma, the volatility.
No, that is the mean. I show the mean. Yeah, yeah. I also have some simulations showing the exact trajectory, the noisy trajectory, but I didn't include in the presentation here. Okay. So now we have a case study of using the alpha potential game framework to study crowd motion games. So finally, I want to talk a little bit on how to study the general stochastic differential games. So here we have like this state transition where the drift can depending on everyone else's position and everyone else's control, and similar for the volatility. And then the value function is in this form depending on everyone else's position and all the players' control as well. So in this case, the alpha potential function will look like this form, where it is governed by the underlying X process governed by RU, and the sensitivity process Y also governed by RU. And in general, this problem is not a very standard problem, because here we involve an infinitely many underlying process X and Y. So here, how we do it is we lift it into a conditional McKean-Vlasov problem, which is depending on, here is a Brownian motion, and here is this R is some random variable, uniform random variable in 0 and 1, and X is governed by both this random variable R and the control. So you need to lift it into a higher conditional McKean-Vlasov problems, and now the control will be with respect to the probability measures. But still, in the linear quadratic, we could solve the conditional McKean-Vlasov problems by reduce the XGB equations into a system of ODEs. Okay. Yeah. So here is the general result for the bound of alpha. So here the C, V1, V2, and V3, they all depending on the asymmetry between the Fy and Fg and Gi and G. The asymmetry in the running cost and terminal cost in terms of the value of first order, second order derivatives. And I want to talk a little bit about this parameter LB, which is depending on the structure of the drift function in the SDE. So in a special case that if your drift function only depending on your own control and your own states in a distributed case, and also for the volatility, then this parameter is 0. So all the other constants disappear. So it also encourages to apply this framework to distributed games because it can some terms just disappeared in this bound. And so here are just some simple examples for the mean field tab interactions, where we assume that the running cost has this structure, that this one is common. It's a common term for all the players. So this one depending on each player's own control, and it can be different for each player's. And this part is also it's depending on the empirical distribution of all the players, but the Fi can be different for all the players. And similar for the terminal structure. And with those sort of the mean field structure, we show that such a game is a 1/n alpha potential game. Okay, so to sum up, here we trying to answer these 3 questions in this framework, in this work. So first, what is the alpha potential function? We construct the alpha potential function using a linear derivative of objective function of each players. And how large is this alpha? So the alpha is characterized in terms of the asymmetry in the second order linear derivatives. And we can characterize alpha for the stochastic differential games in terms of the model parameters explicitly, such as including number of the players, the interaction, and heterogeneity level and cost structure. And in order to find the alpha Nash equilibrium, we lift it into a conditional Makin-Vlasov problems, and we also design some policy gradient method to minimize the function. Okay. So just to talk about some open questions, including some learning algorithm, more efficient learning algorithm for Makin-Vlasov control problems, and whether we can find some sharper estimate of alpha. And now in this work, we focus on the concept of Nash equilibrium, but a different concept of local Nash equilibrium can also be useful in many applications. So can we apply some ideas into different equilibrium concept? And also in many cases, the learning dynamics doesn't converge to a Pareto or Nash, but it somehow end up in some stationary point in between. So can we analyze those algorithm conclusions with this framework? And also some future questions, including the how to find different Nash equilibrium by construction of different potential functions, and in some other applications. Okay, so that is. Thank you.
We have a couple of minutes for questions.
I'm not that familiar with the game setting, but in your this R times U in your integral representation of the phi function, I'm wondering how this, is there like a version of that if we consider like something like optimal stopping problem, where your action is just 0 or 1, or you have like finite number of actions? Is there like a natural serialization?
So for the, actually I have a, so in this work, we consider a case we have finitely many actions and finite state space. So in a Markovian setting, we can, we have some result for the alpha potential game. Yeah.
So then the phi function needs to adapt to.
In that case, we have some different approaches to. So we didn't exactly follow the construction here, but because we only have finite space and finite action, we actually have some other different approach to find a potential function, to construct potential function. Yeah. Thank you.
So for
team problems with identical interests, right? They're always potential games because.
Yes.
So one would expect that if you perturb the team problem just a little bit,
Yes.
you should have some potential gain. But your definition for the Makin Vlasov goes to the other limit. It says that my interaction is as weak as possible. So I'm wondering if there can be a refinement where you allow for still interaction, but you're just deviating from the homogeneity in the.
Yeah, very nice point. So actually, in the Markovian setting, we exactly did the perturbed team game as you you described. Yeah. But for the generous stochastic differential setting and conditional Makin-Vlasov setting, I'm not quite sure. Yeah, but at least for Markovian setting, we have very concrete bound in terms of the perturbations.
I've got one quick question. Is there an obvious way to construct better potential functions that are going to have a less, sort of, a smaller alpha?
Yeah, very nice point. So I think one choice is that here in the integration, we kind of choose we fix a feasible z. You have some, if you want to find some different potential function, first then you can iterate with some choices of z, whether it can lead to you a better value. And also here we consider integration with respect to a straight line. So in our paper, we have a remark that you can integration with respect to a path if the path is regular enough. Yeah.
If there are no more questions, let's thank both our speakers again.